All right, so hey everyone. Today we are going to answer the question, can a quantum computer simulate NMR spectra better than a classical one? So this is maybe a bit of a provocative title, but it is in fact the title of our recent paper on the archive, and my goal today is to give a quick overview of this paper, which I encourage you all to go read to get the details, since of course, we are a bit limited in what we can cover today, but in short, this is a benchmarking study of the NMR solver behind our HQ Spectrum software. And the punchline is, it gives very accurate results for basically any standard NMR parameter regime you could ever care about. And because its resource scaling is designed to be inherently linear with the total size of the molecule, this has some pretty significant implications for the possibility of quantum advantage in the context of NMR. So let's get right into it. So at this point, we've all been through a whole bunch of what is NMR talks. So in the interest of time, I'm not going to belabor this a whole bunch, but just to recap very quickly here, we all know in a standard proton NMR experiment, we take a sample of a molecule, put it in a large magnetic field, subject it to various magnetic stimuli, and after which we measure the magnetic response of the excited hydrogens and measure this and transform it to frequency space. The resulting spectral function, which we can also write in terms of the eigenstates of the nuclear spin Hamiltonian, has peaks at the Larmor frequencies of these nuclei, which helps us identify the specific molecule, and the way that these peaks split apart can also help us learn something about the global structure of the molecule. And for the purposes of understanding the benchmarking results, the two most important terms we need to understand today are the broadening, which models a finite detector resolution and determines the width of those peaks, and the reference frequency of the experiment, which is a frequency that all of the other Larmor frequencies are defined with respect to, with the differences between those frequencies being on the order of parts per million, measured in terms of this so-called chemical shift, delta. So, okay, the spectral function is very important, but how would we try to compute this in a computationally reasonable way on a classical computer? Well, as is the case for many such approximations, our trick for this is to use a clustering approach. The main idea is to write the spectrum as a sum of these so-called spin-resolved pieces, which are supposed to reflect the contribution from a given spin. And if we can focus somehow only on the most important neighbors of that given spin, we can build a so-called cluster for it and try to use the eigenspectrum of that cluster to approximate its spin-resolved contribution. Now, it's important to note that this approach should scale at worst linearly, since we have one diagonalization per spin we have to do. And it may even scale better than that if some clusters happen to coincide, or if there are certain additional symmetries of the molecule that we can exploit. Of course, for this to work, we have to actually have some kind of way to choose which spins are the most important. And while there are many ways we could do this that might have varying performance, the short story is we find pretty good results from this expression here, which is motivated by a first-order perturbation theory and takes into account not only the couplings between the spins, but also the differences between their Larmor frequencies. Now, you might notice that this metric could be perhaps a little less than useful if a lot of the potential coupling terms are actually zero. But for now, let's just see how much progress we can make with this simple idea and come back to that possible issue later. So that's the idea. Now let's get to the whole reason we're actually here. How well does this actually work? So before we can answer that, we need to explain how we actually determine the accuracy of the approximation. Or in other words, we need a metric for comparing the exact spectral function of a molecule with a given approximate calculation. And for our purposes here, we will use the so-called cosine similarity, which we can think of, if you like, an inner product on the space of square integrable functions. This is actually a pretty good choice because not only does it not depend on how we normalize either of the functions, which is something we generally don't care about, but it also doesn't change if we make a linear shift of the frequency variable. And so to get an intuitive idea for what this metric actually means, we can look at the spectrum of limonene shown here, which is a molecule with 16 hydrogen nuclei. And at a reference frequency of 80 megahertz and a broadening of 1 hertz, we see how the approximation at cluster sizes of 5, 10, and 15 compare with the exact calculation at 16 spins. And I would say that we see relatively poor, then good, and then I would say excellent agreement, respectively, which corresponds numerically to error values of about minus 1.26, minus 2.62, and minus 5.25. And so note we're actually plotting here the logarithm of 1 minus the similarity, since the similarity is usually actually pretty close to 1. Okay, so now that we understand what the error metric is, what it means, let's start benchmarking. And we're going to start this by looking at the performance of the solver on these 3 molecules shown here, all of which have 16 spins. So we did this benchmarking for 3 frequency values ranging from 400 megahertz, which is pretty standard for NMR experiments, down to 80 megahertz, which is common maybe for a benchtop experiment, and 20 megahertz, which no one really does, to be honest, but we figured, hey, it's a good test case anyway. So in addition to that, we studied broadening values of 1/10 of a hertz and 1 hertz, which, to be honest, are both pretty unusual, especially for 0.1 hertz is a bit unrealistic, but, or at least anyway in standard NMR experiments. But hey, it's a good test case nonetheless. And so what we're looking at here in these plots is the error of the approximation against the exact solution as a function of the cluster size in all of these 6 possible regimes. And while we see this here for these 16 site molecules, the paper actually shows this for a couple of more. But generally speaking, I would say we see pretty good behavior for both limonene and camphor, especially as we increase the frequency, the broadening, and the cluster size. And for those 2 molecules, we pretty quickly get to an error level, which honestly would be probably perfectly sufficient for any practical purpose you care about. The paper discusses the computational resources in a little more detail, but generally we're talking about seconds to minutes to do these calculations, with maybe the worst case taking an hour. But we do notice, if we look carefully, that one molecule, triphenylphosphine oxide, is maybe not converging so well, even at higher fields. And the paper gets into this in a little bit more detail, but basically this is because this molecule, which you can see here on the screen, is very symmetrically structured around this central phosphorus atom, which couples very strongly to most of the hydrogens, but not the outermost ones. And so the clusters for those spins are missing some important global information. And so we'll come back to that issue in a little bit, but the main thing I want to point out is that other than triphenylphosphine oxide, for these other 2 molecules, we don't actually see any so-called false plateaus where we settle down onto a bad value of the error metric, which would correspond to a case where it looks like the spectral function is converging to a stable solution, but that solution is actually wrong. And so that's actually very important because it lets us benchmark larger molecules where we don't have an exact solution. And so we can do this by finding the largest cluster size we can reasonably simulate, in this case 17, and set this as our de facto correct solution. And if we then compare our approximations at lower cluster size to this reference size, and we see small values of the error metric, it means the spectral function is settling down as we take bigger clusters. And if we then assume that this means it is settling down to the correct solution, which is hopefully a good argument as long as there's nothing maybe weird about this molecule, then okay, we have our answer. And this is exactly what we do for a collection of larger molecules in our parameter database for the same experimental regimes, which is what you see here. These molecules have sizes that range anywhere from 20 up to 50 spins. And once again, I would say we see pretty nice agreement. However, there is something a little bit weird in this data that you might have noticed. At low line width for this one molecule, tert-butyl phosphine, which I'm just going to call diphosphine, And so the obvious question is, what is going on with this molecule? So looking at the spectrum of this molecule for these cluster sizes, we see that this behavior seems to result from the location of some very small peaks in the spectral function at high chemical shift values. And those locations seem to oscillate back and forth for some reason with even and odd cluster sizes. So this is maybe a pretty small detail of the spectrum, and we might be tempted to ignore this, especially since like 1/10 of a hertz is pretty unrealistic anyway. But this is actually another molecule with some pretty weird properties. Again, we have some phosphorus nuclei in the middle of the molecule which couple strongly to the hydrogen. But it turns out that none of the hydrogen actually couple to each other directly, but only the phosphorus which is closest to them. So this molecule is a little bit unusual, and maybe we should be suspicious about whether we really have the correct solution here at size 17. And now, fortunately, in this case, there are actually some additional symmetries of this molecule, which we talk about in a little bit more detail in the paper. But long story short, even though this molecule has 22 spins, these symmetries let us get the exact solution, which lets us see that something has indeed gone wrong. So once we reach the exact solution at the full system size, we see that a large fraction of those two peaks at low shift, the weight has been transferred into a bunch of other features, none of which are captured at smaller cluster sizes. And the solver also struggles to really pin down the location of those peaks at higher shift, small as they might be. So clearly, we need to think about making some changes to our basic method. However, fortunately, it turns out that a pretty minor extension to our method actually fixes things up pretty nicely. So again, the paper goes through this in a bit more detail, but our goal here was not necessarily to find the best possible clustering alternative, but rather to see if we could minimally extend the method we already have and see how well that works. And so in essence, what the extension is doing is identifying cases in which a large number of missing couplings leads to a difficulty in being able to rank the importance of the neighbors of a given spin. And in those cases, it determines a so-called secondary spin, and then it uses this to help build the cluster in a similar way. And while it may not be the absolute perfect method, it does seem to work. With this minimal extension, we can now more or less solve the case of diphosphane. This is now giving us more or less the correct qualitative features already at pretty small cluster sizes. And the same is essentially also true now for triphenylphosphine oxide. This is also converging much better. And this is perhaps all the more impressive, considering that diphosphane was a molecule that Kuprov himself told us was very hard to simulate. And now we can solve it in a few minutes on a laptop. So, coming back to the title of the talk, what does all of this mean for quantum advantage? Well, to put it bluntly, the fact that we have a linearly scaling method, which as far as we can tell seems to perform well in basically any realistic parameter regime for every molecule we've tested, definitely casts doubt on the idea that we could see quantum advantage in standard high field NMR experiments. Now, you might argue that maybe there is some molecule or even maybe a couple of molecules out there somewhere that are unusual. They have a practical use, and somehow even if we try to fix up our solver is not going to work on them. And that may be the case. However, then you would naturally have to ask, is building up the entire industry of quantum computing for NMR worth it for a handful of molecules? So that is the situation, I would say, for high field NMR. However, the fact that our solver struggles a bit more at low fields and lower broadening suggests that maybe you would have a bit more luck looking for quantum advantage in those regimes. And while that's not really applicable for standard NMR experiments, it is for so-called zero field NMR, which is a subject that goes beyond the scope of this talk, but it is a potentially interesting case to consider, and hopefully we will have more to say about that soon. And with that, it is time for questions. So Thank you, everyone, for listening.